Incremental launch erection of a steel girder bridge that we were fortunate to work on over the last few years. The project's in this US460 over Pond Creek in Pike County. This picture shows a little bit of the first launch. Actually, into the second span. I just want to show you a few pictures of the site just to give you a handle on what the site looks like. The terrain here is awesome. The piers are about over 300 feet tall, the tallest piers. Two huge cuts on both sides. And this project was kind of planned and expected to be launched, erected during this development. This was, of course, prior to the launch. The piers in place and the girders not there yet. Okay, so project is located on US460, part of a larger project connecting through Virginia. The owner's Transportation Cabinet District 12. Contractor is Bush and Burchett from Allen, Kentucky. My company Stantec did the erection plan design, and the original bridge design was by Palmer Engineering. It's twin bridges carrying 2 lanes each direction. Total length of about 1,000 feet. 5 spans, the longest is 220 feet. Piers are over 300 feet tall. The tallest piers. The profile grade is straight, tangent 1%. The plans require the contractor to provide an erection plan by a licensed engineer. Those are our role in the project. Bush and Burchett we worked with before and contacted at Stantec prior to the bid to discuss the launch erection method. Stantec provided pre-bid evaluation of the girders for the launch and equipment requirements for the launch. Contractor preferred this launch erection method due to the site, the tall piers. There really was not enough working area under the bridge to erect it conventionally. It's so tall, not much footprint down below to put cranes and deliver the girders and so forth. So they fully expected to launch the bridge. They really didn't want to build it any other way. The letting was in May of 2017, just for the bridge. The roadway was already in place. The total bid was $27 million. It's about $300 per square foot of deck. Not a cheap bridge. Structural steel is about $9 million of that. About 2 million pounds of steel in each bridge. Here's the plan sheet of the layout, bridge layout, showing the grades straight. Both the bridge is straight horizontally and the profile is straight, which makes the launch much simpler. There is a slight vertical curve on the right end of the bridge, the abutment 2 end. There's a picture similar to that plan sheet showing the piers complete. The piers are not the focus of this presentation, but after the bid, the contractor asked us to look at another way to build the piers. The piers on the plans were rectangular, hollow shaped. It's been used quite a bit on this route and others in this area. And he's built plenty of them. But he asked us to evaluate an alternate method to simplify the forming. The tapered hollow shape was difficult to form, especially on the inside. So we developed an H shape, we call it, section that allows all the formwork on the outside and varied the width of those pieces as we went up. And that worked out well for them. We're happy with that redesign. It was done as value engineering. The incremental launch is kind of explained here. This diagram at the top, the bottom row shows the finished grid with the 5 spans on the right, and the left side is the work area where we erected the girders in the cut at the bucket. So starting at the top of this diagram, the first step was to erect 3 of the steel girder segments in that work area, along with the nose piece on the right and a tail piece on the left of the launch. In the next step, we pushed the bridge to the first pier, and then come back and add 2 more steel sections behind that, push that to the next pier, and so forth until we completed the bridge. 5 launches per bridge. Stantec prepared the erection plan in 3 phases. I won't go over those here, but the initial goal was to get the steel girders ordered. So we had to get the girders checked and approved for this launch. The submittals were reviewed by Transportation Cabinet and Palmer, original designer. We checked the girders for the cantilever condition, kind of the picture that you saw earlier. The girders would cantilever out over the pier before they reach the next pier, so that was one of our primary concerns. We checked that using various methods, including the stability design, checking for buckling. We used 3D analysis to get the forces in the girders, and surprisingly, the girders were strong enough to carry this cantilever case. It was surprising to me, at least, that we didn't really have to strengthen the girders to carry this. And we did check the girders for their final condition as well, just as part of our check. We had to make some revisions to the framing for the launch. We added temporary lateral bracing for the full length of the bridge on the top side and along the bottom of the girders for the first 2 field sections and part that would be in cantilever. The bottom flange width, we wanted it to be constant so we could use lateral guides to control the horizontal movement. So we changed the width of the horizontal width of the bottom flanges to 24 inches constant across the whole bridge. The bottom flange thickness transitions we changed. I'll show you a picture in a minute. We changed the flange splice to allow the roller bearings to pass. And because of all these changes, the department asked us, Stantec, to take responsibility for the girder design, for the project. We expected that. Here's the framing plan and cross section of the twin bridges, 4 girder lines, spaced at 12 feet. The lateral bracing down the center of the bridge there was temporary, just for the direction. Those are removed after erection. Here are some of the changes we made to the girders. Top picture there, they're typically the bottom flange transitions, the thickness transitions occur outside the web on the bottom of the girder. we're gonna roll this across rollers, so we wanted to make a smooth surface for the girders to roll. So we took that transition and flipped it upside down for the bottom girder. In the middle left of the screen, you can see that transition. Steel fabricator had a little concern about this. This is difficult for them to fit up and weld with those transitions cut into the web piece. But after they had an issue on one of them that I'm aware of, and after that they were able to make that work. On the bottom left is the bottom flange splice. You left a gap in the bottom flange splice to allow the rollers to pass by the splices. And then just to the right of that, we changed the width of the bottom flange to be constant. Here's the work area at the abutment one. We had to undercut the road was already cut for the road. However, we needed to cut it deeper in order to put the girders together at their approximate final elevation. So they had to cut about 10 more feet of rock out in this work area, about 400 feet long and 10 feet deep. We built 4 temporary vents, we call them, for the to erect the girders on. This shows the nose piece on the right that we added for the launch. The purpose of the nose is to allow for the girders to deflect as they cantilever. We estimated deflections of about 4.5 feet, 4.4 feet it says, for the longer span. Shorter span, the end span is about 2.2 feet of deflection. So there's about a 5-foot taper in that nose piece to accommodate that large deflection. On the left is the tail piece added to the back end of the girders. The purpose of that is to distribute the jacking load to each of the 4 girders equally. It also has a taper on the bottom of it to allow it to roll off of the support gracefully without just dropping. To move the bridge, we use the Strand jack system. Equipment is by Interpack, and it was provided by Engineered Rigging from Valparaiso. We had 2 each Strand jacks, hydraulic pumps, Strand guides, and Strand recoilers. This is a standard system that the picture on the lower left is a common use of this equipment for vertical lifting, but we kind of adapted that for our purpose to do a horizontal pull. The system is controlled by a laptop computer, and Engineered Rigging provided a technician to operate the system. Very helpful. We designed, Stantec designed special frames to support this equipment at the abutment. This is at the abutment 1. There's 1 jack on each side of the bridge at the exterior girders. Jacks are 70 ton service load capacity with up to 7 strands. We only used 4 of those strands and estimated to pull at about 36 tons. The jack stroke is about 18 inches. And when it was allowed to run in automatic mode, it could move the bridge about 1 foot per minute. Here is the most important guy on the project on launch day. It was the Engineered Rigging technician operating the laptop and controlled the equipment. This screen is on the left there. It shows force in each jack and the amount of movement per jack. That the computer kept the movement equally on each side of the bridge You can monitor the forces. The forces weren't always equal from left to right, but it never really seemed to be a problem. This was the first launch, I believe, done in November. It was cold weather, and having a laptop computer out in 20-degree weather is kind of odd, but it seemed to work fine. The other part of the movement system was roller bearings. Stantec designed this system using standard Hillman products. The Hillman rollers were purchased by the contractor. They don't lease those. We use two different sizes, 110 tons and 75 tons with the piers and the buttons. We use a rocker base to allow the roller to accommodate the cantilever deflection, especially, and other minor deflection, minor rotation of the girder. We designed the system for 5% friction based on Hillman's guidance. However, during the launch, we observed quite a bit less than that. It's only about 2% friction that we were observing, plus the 1% grade, a total of about a 3% force to move the bridge. For the interior girders, we used lateral guides to keep the bridge horizontally controlled. These were also at each support. We designed this bracket. The contractor fabricated these pieces. The roller itself is provided by Hillman. Here's a view of the roller and a little video showing how easily these roll. Here's a video. This is real time during one of the launches, showing how the girder moves. Slowly but steadily. You can see here that the roller is between two of the splice plates. One of the lessons learned here is next time we will give them more clearance between that roller and those splice plates. At times they had issues with those jamming up, rubbing, or impacting the roller. Another observation we didn't really predict, but they were able to work through it. The girders have about 4 inches of camber built into them for the eventual deck deflection. So as they move, that camber moves the girder up and down, and it's enough to pull the girder off of the rollers at the work area. They would come out as those lateral guides that we just saw, and at times it was difficult to get them. It was a little challenging. They had to pause to get them to go back down between the guides. They would use a come along or a excavator equipment or something to push or pull the girder sideways. So that was a little bit difficult. It didn't really hold them up much. We finally just kind of figured out a way to deal with that after practice. Here's a view of the tail end during the launch and a video showing that the taper works and it comes off the roller bearing without dropping radically. This picture was taken during the second span launch. You can tell that because of the excavator there. The first launch, we did not have an excavator back there. And as this tailpiece, as we started the launch, the tailpiece taper caused the girder to move on its own about 6 feet. kind of alarming to the contractor, and we had not predicted this as well. It didn't move out of control, but it moved on its own without helping the jacks. So from then on, they put an excavator behind the tailpiece to kind of hold it and not have that uncontrolled move. Some general comments. There's a total of 7 cranes on site, all of them owned by the contractor. There's basically one at each pier. And then several in the work area to erect the girders. Approximately 10 workers on site. The erection of the segments took a variable amount of time. They got better at this as they progressed. It took about 3 weeks initially. They got that down to 1 or 2 weeks toward the end of the project. The tail pieces end up needing to be disassembled and reassembled between each of the launches. We had assumed, or I hoped, that they could just take that piece off in one piece, but it didn't work out that way. The girders bolt together very tightly at the splices. So one of our concerns was whether the camber would come out the way it was intended. And it did. The splice, the bolted splices are, you kind of get what you get. There's not much play in how those things can go together. So that turned out to be less of an issue than I was worried about. We measured the girder cambers in the working area, and they were generally less than a 1/4 inch difference between the girders. Because of that slight difference, we left the cross frame bolted connections to the girders slightly loose to allow the girders to allow for that 1/4 inch difference, for example, as they pass over the rollers. Otherwise, if those cross frames are tight, the loads on the girders would not be equal, and you could have issues with overloading bearings, roller bearings. So that was a little bit of a challenge for the contractor to leave those connections loose initially during the whole launch, and eventually as they put the deck forms on, they tighten those cross frames as they move across the bridge to put the deck forms on. The girder spacing was slightly larger than the plan showed, just due to fabrication tolerances. This is probably the cause of some of the rubbing I mentioned earlier about the splice plates. For the eastbound bridge, the first launch was November 23rd of last year. It took about 4 hours to launch the first span. The next launch was in December. It took about 6 hours for span 2. The others were similar. The final launch was in February. Westbound bridge was started in April this year, and finished in early June. It went expectedly a little smoother than the first ones, faster between the launches mostly. During the launch, the contractor had people looking at the roller bearings for conflicts at the splices, looking for the lateral guides lifting up, and then checking the nose piece when it reaches the pier for its horizontal and vertical position. Here's an overall view of the work area taken from the drone. We were on site just the first 2 launches, and I have several pictures that I borrowed from John Michael Johnson for the days that we went out there. Here's the initial part of the first launch. showing the deflection of the nose piece. There's the span 2 launch. This second span launch was the moment of truth to see how well our deflection calculation turned out. There's a question in another session about this. It was nearly perfect. We on the picture on the right here, you can see the girder nose approaching the roller bearing, and it's going to hit just barely enough. We had planned to have nearly a foot here extra. It didn't happen for a couple of reasons. One of them was the nose piece nearest us here was constructed a little bit too low, about 4 inches lower than the other nose piece. So that's why this side was a little tighter. But anyway, it was just enough to clear the rollers. These pictures are taken by the contractors personnel. I was not out here on the pier, but it was an anxious moment. Standing at the abutment to get these pictures and hearing from them. Picture on the left shows the horizontal position of the girder as it approached the pier. Those came in very good. Generally, the horizontal position was within about 1.5 inches or less of its intended position, and they used winch, cable winch. The workers, 2 workers here on the nose pier, and they could pull the system left or right as needed to fit in the guides. Here's the nose piece reaching the abutment 2. And then after we launched all 5 spans, the permanent bearings were already in place, so we jacked the girders, took the temporary bearings out, and lowered the rig onto the permanent bearings. We did that one support at a time. I did the abutment, then the pier, then the next pier, and so forth. Finish up here, I just have some photos and videos and this just shows the site and the awesome view height of the structure here. The crane, the articulated crane there is about 400 feet tall. They use that crane to reach Pier 2 and Pier 3, the tall piers. On the launch days, they really didn't need, they needed one crane to move somebody to the pier. The launch days were very quiet. There was no, that crane was down the hill from the work area, so it was kind of a pleasant work site, actually. Here's a time-lapse view of the first span launch. On the right, you can see the jack and the recoiler working. The jack feeds the strands out the back and pushes it. The guide pushes it back into that wheel recoiler. That system worked pretty well. And you can see the nose pick up the girders as it reaches the pier. A few spectators on these first 2 launches. Here's the second span launch. They had some issue with the roller on the splice conflict, and that's why this was a long day. We were monitoring the deflection as we went. We knew it was going to be close, but couldn't wait to hear the actual result when the nose got there. So that's the end of that's the launch to the second pier, the one with the 4-foot deflection. This is from KYTC website, webcam, sorry. Back that up. Show it again, you can watch the nose deflect here. This, the District 12 has a project website for this and a webcam that I got this picture from. Been very interesting to monitor the project from that website. Here's a view of the first bridge complete. And some pictures from John Michael's group of the overall project, showing the height of the bridge and the limit. This is with the eastbound bridge complete in the background and the westbound bridge just beginning to be launched. And some pictures I borrowed from John Michael. Showing the height of the piers on the ground. The completed westbound bridge. And here's a picture from last week. Current position, they have the deck forms on the interior deck forms on both bridges. And on the right bridge, you can see the outside deck forms are in place. They'll be pouring the deck or putting rebar and pouring the deck soon. We chose to pour the second bridge first because of the access problem or access limitations with a crane. So they'll pour the right bridge, the westbound bridge first. And once that deck is ready, they'll use that deck to hold equipment to pour the eastbound bridge on the left. I mentioned the district's project website. It's US460 online. Very nice website for this bridge and the project in general. The left picture there, the button on the bottom left, you may be interested to look at some of these pictures. The button on the left will take you to the concrete webcam that has some of the pictures I showed you and many more. The screenshot on the right is from that. You can pick time lapses. I also encourage you to go to John Michael's presentation. If you didn't go this morning, it's right after lunch, I believe. He has a little more information and more pictures, more interesting videos, including the launch of all the spans. So with that, that's the end of my presentation. Happy to answer any questions.
You have to monitor the piers for deflection?
Yes, we did. One of the concerns was as the nose reaches the pier with that taper on it, pushing the pier. So yes, that was one of the things we monitored. We used survey to measure that. Those deflections were considerably less than we expected, partly because the friction was less, and partly because I think the concrete in the piers was stronger than we estimated. So those deflections were on the order of 4 or 5 inches. One of the concerns was, would the pier recover that deflection? Would it stay permanently pushed or not? and it did recover to its plumb position. So yeah, that's a good question.
David, was there any grade on the bridge?
So 1% grade, straight grade, which, yeah, makes it easier to launch. We launched uphill purposefully. And thankfully the profile was straight, tangent. Yeah. So, there's a slight vertical curve on the abutment 2 end, which was curved in the right direction up. So that helped a little bit. I would encourage you to go to see John Michael's presentation. He has even more pictures if you're interested.
Right. Thanks, David.